I would like to deliver some notes to you. Work and kinetic energy. And before we get into all this, I do want to just introduce to you here, this is a concept that you might know already from calculus, depending on where you are in your calculus course. The idea of slope is really important. So if you have, for example, the graph of a derivative function has a lot of information in it, and the physics, the most obvious physics analog to that is a velocity versus time graph, because velocity itself is the derivative of position, right? So if we had, for example, a velocity versus time graph that looked like this, the slope of this is the acceleration. By definition, we define the acceleration to be the rate of change of velocity versus time. And there's another thing, there's another characteristic of this graph that we are interested in, that we will be interested in, as soon as you have the calculus vocabulary to talk about it, and that is what we call the area under the curve. So what that means is from your curve and then get horizontally to the axis. So if you had like a negative velocity here, you would bring that up. So the under the curve doesn't actually mean that you have to be going down. It's between whatever your curve is, or line in this case, and the axis. So here, if we were talking about from time 0 to time whatever that is, we're talking about the area of that. And what does it mean? Well, let's see. In this particular case, we could figure out what the area of this triangle is. It is t wide, right? T1 wide, and it has a right here. Well, let's see. Slope is rise over over run, so that means that A is equal to the rise here over run, which means that this rise right here is equal to AT. If we take T to be the AT1, I guess. So this is T1 wide, this is AT1 high, and let me just write out what I did there in case that wasn't clear. So slope is equal to rise over run, and I know two of these things, so that means that the rise is equal to slope times run, which means that that rise is equal to slope, which is A, times the run. So that means the area here of this, I started to write it here, but I'm going to move down where I have a little more room since I crowded up that space. That area is equal to 1/2 base, which is t, times height. And there's no initial velocity here. If there was, then this area would be like sitting on a rectangle that would be like vi high and T1, so I'm just going to put in parentheses here. If this was raised up there would be a rectangle underneath it that was VI high plus T wide. And that should look real familiar. That's your displacement. So anyway, that is just to say that in general, the two characteristics of a graph that we're interested in are the slope, which is what we've been studying in calculus so far, all these derivatives and everything, and then also the area, which is the next big chunk of calculus that we're going to be interested in, or maybe you've already started to cover that in your calculus class. So slope and area are very important in calculus, and they're important in calculus because those things have physical meanings when we have graphs that have some kind of physical meaning themselves. So think about that for a minute, or put that thought, file that away in the back of your chaw, and let's consider a graph where a force is applied through some distance. And let's just take the very simplest case where that force is constant. So the slope of this is 0. That's not very interesting. That the rate of change of the slope would be like df dx, right? I mean, that's what we would call it in calculus terms, so that's not very interesting. But what about the area? What's that? Does that have some kind of physical significance, or can we assign some kind of physical quantity to this? Would it make sense to do that? So if we look at that area here, there's my constant force, and here's some displacement, delta x. So that area is equal to, it's just a rectangle, so force times delta x. And we could play around with that some. We could say, okay, well, force times delta x, since this is a constant, it's some constant force in this case, it's always true if this is the only force that's acting on something. So in other words, if this is like the sum of all forces, if that's really the thing that's constant, instead of just like one force that might be balanced out by something else. If this is really like the net force or the sum of all forces on something, then here, let me just add that. It's talking about the sum of all forces. The sum of all forces is equal to mass times acceleration. And then if this is constant, then acceleration is constant. So that means you can use kinematics equations, but those apply. And there's a particular kinematics equation, the one that says that Vf squared is equal to Vi squared plus 2a delta x. So just observe here, I've got an a delta x here, and I've got an a delta x here. So I could solve for that and make a substitution. Maybe that would be enlightening. So if I do that, I get 1/2 Vf squared, and dividing everything by 2, and then I'm going to subtract that over, minus 1/2 Vi squared is equal to a delta x. So I can make that substitution here. In place of a delta x. So that's equal to 1/2 m Vf squared minus 1/2 m Vi squared. Well, that's interesting. So what does that tell us? So we have, if we have the sum of all forces times some displacement, so some unbalanced force. Of course, if this is 0, then that's not very interesting. We have the sum of all forces here times some displacement, and that is equal to 1/2 mvf squared minus 1/2 mvi squared. And I should just note here, for this all to be completely correct, this is the sum of all forces in that x direction. I'm only just thinking about one dimension right now, so everything's happening back and forth on a line. We'll generalize in a minute. Okay, so this is where the game of physics and I suppose science in general to a larger extent, one of the things that we humans have to do, there was no magical like first physics book hiding under a rock somewhere in the forest in Vermont or I don't know, whatever. There's nothing like that. We had to make up all these ideas and names for things. So if you want to just take a step back and think about what we've done so far, we did from the very beginning. In Chapter 1, we thought about what kinds of things we can measure and what units we would use to measure those things. And then in Chapter 2, we looked at positions and then what happens if the position of something is changing. We defined velocity and we defined acceleration. But we defined those things. Those are physical quantities that we came up with the definitions for. And we went from there, mass and so on and so on. Now, what we do in a situation like this, there's a lot of suggestion here that we should be open to. This equation right here is telling us that if you have a force, an unbalanced force, that acts on an object through some displacement, and you take that unbalanced force and multiply it by the displacement, you get something that's equal to this quantity 1/2 mvf squared minus 1/2 mvi squared. Of course, that's the same as delta 1/2 mv squared, right? Because the mass of the object is the same all the time, so this would be the same as this. So these things, we could just go about our business and leave these things as such. But there's a very strong suggestion here that maybe these are physical quantities that deserve to be named and considered as some like special for us, special enough that they deserve names. And they are. So this right here, a force applied through a displacement, we call this work. And since it's the sum of all forces that we're interested in here, this is the net work. Not to be confused with the word network, which is something else. The net work. So we think of work as something that's being done on an object. Like if there's an object here and like some force comes along and acts on it through some displacement, then work has been done on the object by that force. That's equal to this, delta this thing, and this 1/2 mv squared, that we're going to call kinetic energy. So there you go. That is a theorem, sometimes called the work kinetic energy theorem, and it's a good one. So what are the units of these things? Just add that here underneath. Units here. Well, this work we got by multiplying a force times a distance. So force is measured in newtons, and a displacement is measured in meters if we're doing our SI units. And if we're going to call this kinetic energy, this is a little bit of circular reasoning here, which you're just going to have to tolerate. This here is, let's see, 1/2, that's just a constant, and then the mass is kilograms, and then this is a velocity, but it's getting squared. So it would be equal to that. And of course, that is consistent if you think about what a newton is. A newton is a mass times an acceleration. So a newton is a mass times an acceleration, and then times that. And then you put those together, and you can see that that is consistent. But this unit right here is just in the same way that this gets packaged together, and we call this a Newton because we don't want to keep saying kilogram meters per second squared over and over and over again. This is all packaged together, and that is called, well, you know what it's called. It's the unit of energy. That's called a joule. Capital J is the abbreviation for that. All right. So let's see some details, some things that you need to know. Work. Is equal to a force times a displacement. For whatever reason, usually when we're writing out this work, we write this as a D, but you could think of it as a delta x, that's fine. But this is only true if they're in the same direction. So what if you had a force that's acting on an object that's pointing in this direction, but the displacement that it goes through is in this direction? Well, the only part of the force, only the component of the force that's in the same direction as the displacement. So in other words, we have to kind of like reduce it back to our one-dimensional case that we were thinking about on the previous page. So only this part right here of the force is the part that's really doing work on this object through this displacement. The part that's going this way, well, I mean, the object's moving this way and that force is going that way. That's not doing any work. It's only this part. So if theta is the angle between those, then this component right here of the force, that is F cosine theta. It's that adjacent to that angle component. So the work is equal to force times the displacement times the cosine of the angle between them. And I usually put that in parentheses because the angle between them if the angle between them is 0, if they're pointed in the same direction, then you just get the whole thing. I'm not really going to push too much, to the dismay of some physics teachers and professors, possibly. I'm not really going to push vector operations too much in this course. I think it tends to, in an intro physics course such as this one, I think it can obscure the real business, what's really going on. So I do want to point out to you, though, because you do know this, you have seen this before, that the force, if you have one vector and another vector, the magnitudes of those, and you multiply by the cosine of the angle between them, that is the definition of the vector dot product. I don't know if you remember this from pre-calculus. I think that's when you see this. That there's two different vector multiplication operations. There's a dot product and there's a cross product. Cross product, we'll talk about that sometime later in the course when we get to more rotation stuff. But for now, I can just remind you that this is the dot product, but this is what it means. Right? When you see vector dot vector, this is how you actually do it. There's other ways of finding it. Maybe you remember that from last year too, but this is what we're going to be up to. All right, let's see. What else do I need to tell you for right now? For right now, I think that is pretty much what you need to know. So this is also true for, let me just put a little box around this, and I'm going to put an asterisk here, and then I'm going to put an asterisk here. This is for constant force. There's another definition for this when the force is not constant, and it's going to depend on some calculus knowledge that you may or may not have right at this time. So I'm just going to, I'll preview that, whether you know this or not. In general, since we're saying here that work is force times distance, that would be this area here. And it turns out that work is this area underneath the force versus displacement graph, whether it's a horizontal line, in other words, constant force, or not. It doesn't matter. So if our force is some kind of variable force, it's still the area under that. And that's something that you learn how to do in calculus. Maybe you already know how to do it. Maybe you're going to learn how to do that sometime soon. So this, to say that it's just force times distance, that's all fine and good if it's a constant force, because then it's just a rectangle and the area is very easy to find. So more about that soon when we know for sure that you have the calculus under your belt. I think that is where we're going to end those notes for now. Alrighty.